Hello everybody, we're here to talk about linear motion, that is, motion on a line. So, I'll include this Mathematica sheet, but I've just put together a simple number line illustration. We'll say these numbers down here are in meters, and so we're along this line, along the ground, we can say we're moving forward or backwards along this line, but not in any other direction. We have to stay on the line. Positive will be forward, negative will be backwards, and those are the two directions which are kind of the same direction but inversed that we can go on. So let's get right into how we do this mathematically. So we can look at the simplest example is stationary motion, where we have a puck. I'm using an ice hockey puck on an ice rink as an example, since it's pretty close to frictionless, at least in our ideal case. But we can look at this. So the position in space, we're going to call it x naught. We're measuring it off some axes, some established origin point. And any position in future time, it's not moving, so it's just going to stay at the same position x naught, and I'm going to establish the origin as this vertical line as x naught of 0 meters. So that's the simplest case, but it's not very interesting. More interesting is the second simplest case, constant velocity. So we have time 0 seconds. So imagine we got a clock timing its movement. At 0 seconds, we're at 0 meters, but it's moving at this velocity. Velocity is a speed and a direction. So we are moving at 0 seconds. We are moving to the right at a velocity of v that we will determine. So at t equals 2 seconds, we've now reached 4 meters, and at t equals 4 seconds, we've now reached 8 meters. You may recognize this as a linear equation, linear relationship. Don't take the squares, the spacing on the grid here of this too literally. I did my best, but this is just showing the general idea. They should be equally spaced. So let's do this mathematically. So we've established that the velocity is the change in our position over change in time. You may recognize then that is the slope of a line. So if we put x of t on this axis and time on this axis, so position on this axis, time on this axis, we are just looking at a linear relationship. So we can calculate it. We look at time 4 seconds, go down to, position 4 meters, move over, down, time is 2 seconds, to position 2 meters, over, down, time is 1 second. We calculate that and we get our slope, our velocity is 2 meters per second. Now it's kind of a roundabout way. You may already know the equation for this linear motion, but we'll get the calculus interpretation so we can get that working. So the velocity is change in x at change in t, dx dt. So then our equation for x of t should be the integral of this velocity equation over time. Velocity is a constant in this case, as we've established, so we can just put v times t for the integral and then adding a constant c. And then that is our equation, where if we plug in x equals 0, that'll be 0 in this case. But we're going to title that x naught or x0 because that is our starting position. We kind of established up here when x is 0 at time 0, that is our starting position for this problem. So we call it x naught. And solving like we did, seeing that it's 0 here, then our equation for this particular example is 2 meters per second times time. Pop into Mathematica briefly, look at a few other examples. So here's what we just did. If we were moving faster, naturally, that'll be a steeper slope. If we were moving the same, but if we were at position 3 to start, then we start with our y-intercept at 3 meters, and then we're moving up. And if we were moving in the negative direction, then now we're moving the opposite. Imagine flipping the velocity around. We're starting at 3 meters, and we're gradually moving towards the 0 meter origin point, and then past it off into the negative direction. So that's constant velocity, but we can get just one more step more complicated, but that'll give us our more general equations of motion. So we're instead now looking at constant acceleration, where we defined acceleration as the change in velocity over change in time. So at 0 seconds, 0 meters, as we started before. 1 second, we're at 2 meters, and then at 2 seconds, we've moved much further than we did on the first step. We are now at 2 seconds and 8 meters. So in this case, the linear relationship is going to be between velocity and time, where every second we're increasing our velocity, or every unit of time, that is. So acceleration is equal to delta v over delta t. We do the same integral equation we did before, and we find out that our equation for velocity and constant acceleration is a times t plus v naught. So v naught, where v naught will be our initial velocity, in this case 0. So solving this equation, we get acceleration is 2 meters per second squared, where we picked out the points. So that will be, and so you can note 8 minus 4 meters per second, where 8 meters per second is one velocity we've read, 4 meters per second was another velocity we've read off this plot. So then our unit for acceleration is 2 meters per second squared. Now, logically, if velocity is the integral of acceleration, and as we established before, in fact, I can prove it, even in this case, now I plugged in the equation for constant acceleration here. It's going to have this t squared shape, asymptotic shape. But if we zoom way far in, we see that on a small time interval, as delta t goes to 0, the position time is still going to have this x of t equals v times t linear relationship. So, going back here, we have then if the velocity of time is the integral of acceleration and x, our position, is the integral of velocity, then it stands to reason we just have to do a double integral. And so a of t, once again, we're in constant acceleration world. We are holding down the acceleration on our car at a constant level for whatever reason. Another common example would be a ball falling, neglecting air resistance. And so acceleration is constant. So a double integral of just a constant a. First integral is simple, as we've done several times before, just a times t plus a constant c. Then the second integral, we do integral of just this integral is going to be t squared over 2, if you don't remember. And then we also have to integrate this c constant we've added, so c times t, and then we've added another constant for the double integral. And then filling it, so we can check at time 0, x of 0, both of these first two terms will be 0. So we can establish that this d term is equal to x of 0, so it's equal to x naught, our starting position. Then at position if we take the derivative of this equation, we wind up back with this equation, and at time equals 0, this D, or the C, is V naught as we established before. So, big final equation of motion, x of time is equal to a t squared over 2 plus v naught times t plus x naught. You'll see this equation written the other way around sometimes, but it's the same equation, as in starting with x naught, then velocity, then acceleration. And solving, as we did before, we get the equation of this motion is 2 times t squared. One more equation that's useful for if we're looking to define a relationship between velocity and distance instead of velocity and time. We can use a couple simple facts equations to find that relationship. So the average velocity is actually our initial velocity plus our final velocity divided by 2, as an average is for a linear relationship like this. So over an interval of time. Then acceleration, for once again, it's going to be a constant. We just look at that linear relationship, that slope relationship. Velocity, final velocity minus initial velocity divided by delta t, our change in time. Flip that equation around and we have an equation for delta t. So now what we're going to do is logically, once again, of this constant acceleration, we should have delta x is equal to the average velocity for that time interval times delta t. Instead of doing an integral or something like that, we can just use this average for this linear relationship. So then we substitute our old equation for v average, and we substitute our equation here for delta t, and we wind up with v naught plus vf times v naught minus vf divided by 2a. You may remember that this will simplify to initial velocity squared minus final velocity squared over 2a. And then rearranging, we have enough equation for our final velocity if we know our initial velocity and our acceleration after a distance delta x. So that's one of the fundamental equations, and now we've got them all. Invitation. Sorry about the weird break, had to re-record a bit. But this last bit, bonus exercise, if you want to prove that for t naught doesn't equal 0, so these equations are assuming a t naught of 0 as we're going from 0 time to the end. But if you want to prove for a more general case that the integral between final time and initial time does result in our equation, you can do this exercise that should result in the same t squared over 2 term. The other terms come from the kind of other side of the integral equation. You don't need to worry about those, and it should reduce to, so it'll be a delta t, or t final, minus t naught squared over 2, and it should reduce with t naught goes to 0 to this term. Yep. Oh, other little correction. These numbers you may have noticed were wrong the first recording, so don't pay attention to that. These numbers were always correct, so you can always pay attention to that, but I've now corrected these. Should all be good. Thank you very much.